Unit 12B will be a continuation of our conversation about sound. We now revisit the idea of resonance. We first saw resonance when we were looking at standing waves in a string under tension, and we realized that it was possible to get a standing wave where the waves that we sent through the medium were reinforced by successive waves that we sent through the medium, such that we created a standing wave pattern in that string. This resonant frequency gave us an amplitude that was greater than the individual amplitude of any wave that we originally sent through the medium. So resonance is a phenomenon where we send waves through a medium and those waves reinforce other waves to amplify them and give a wave with a larger amplitude. Essentially, resonance is like an oscillator system that is being reinforced to have a greater and greater amplitude every cycle. This happens when an opera singer is singing to shatter a glass. This happens when we have a driving force that pushes a spring farther and farther as it oscillates. And this also happens in the case of bridges or buildings that will vibrate and oscillate with greater amplitude if we can supply additional vibrations at the correct frequency. Just like we had for the string under tension, where we sent a wave through, it hit a fixed end and was reflected back, and those reflected waves added together with the incident waves that we were continuously sending through the string, you can also get a very similar situation for sound waves traveling through a medium. And instead of thinking about a string fixed between 2 points, let's think about a column of air or a pipe that is filled with air that we send a sound wave into, so that those air particles will then be compressed and rarefied according to the oscillations of the sound wave. The case that we're going to look at is a tube that is closed on one end and open on the other end. There's a lot of musical instruments that have this open-closed configuration that we're about to talk about. In a tube that has one end open and one end closed, the closed end acts like a fixed point, whereas the open end acts like a free point. And so if we were to get a standing wave for a sound wave in an open-closed air column, we would need to have an antinode for the wave at the open end and a node for the wave at the closed end, because those mimic free and fixed points respectively. So for this tuning fork, if we send a wave into it and that sound wave propagates, hits the closed end, and reflects back such that we have a node at the closed end and an antinode at the open end, this sound wave will resonate and it will create a louder sound. The individual sound waves that we send into that pipe will reinforce each other to make a resonant sound. This is actually how a huge variety of instruments work. Most woodwinds and brass instruments have one end that is closed and another end that is open. So for example, a saxophone, clarinet, trumpet, tuba, anything like that would be an open-closed air column. But maybe one that you're a little more familiar with is the human voice itself. There's one end that is closed where no sound vibrations actually would be heard, and another end that's open where sound waves are heard and sent out with a maximum amplitude. Just like we had for the string under tension, there is a way to calculate what resonant frequencies will be allowed for creating standing waves in an open-closed air column. And these resonant frequencies start at the fundamental frequency. That's the lowest resonant frequency that we can possibly get in an open-closed air column. And those frequencies will then step up to higher level modes, which we call overtones, or higher harmonic modes. The resonant frequencies to achieve a standing wave in an open-closed air column can be determined using this equation here, where we once again have our harmonic mode number. This can range from a variety of integers. We have our wave speed, depends on what temperature and what medium you're traveling through. And we have the length of the column itself, much like we had the length of the string itself. However, it is important to note that for an open-closed air column, the only standing waves that would be allowed or possible would be ones that had a harmonic number that was an odd integer. This is different than we saw previously. For open-closed air columns, the first harmonic mode, the fundamental frequency, would be achieved with a harmonic number n equal to 1. However, the second harmonic mode, the second standing wave that we could possibly get, would be called the first overtone, and that would correspond to an n equals 3 harmonic number. So if we wanted to look at what some of the standing waves might look like for a sound wave in an open closed air column, we can see the fundamental frequency is shown here with a node at the closed end and an antinode at the open end, and we can step up to higher overtones and still get a standing wave pattern that has a node at the closed end and an antinode at the open end. This is what the second harmonic mode would look like, or the first overtone, the third harmonic mode, and the fourth harmonic mode. Remember, these open closed air columns will have harmonic modes that don't necessarily match the number n. This first mode has an n equal 1. The second mode has an n equals 3. The third mode has an n equals 5. And the fourth mode has an n equals 7, and so on. If you want to try to see a GIF to show what these sound waves look like, it's very hard to visualize because we're talking about air pressure, which is something that you can't really see with your eyes. But these GIFs sort of show what we're getting at here. The fundamental frequency would be shown somewhat like this. That one's really hard to see what the air particles are actually doing, but you can see how that the amplitude oscillates. In the second mode, you can see that there are places where the wave is rarefied and compressed, which sort of matches closely to what you see in the graphs below. And then we step up to higher level harmonics from there. So that was for an open closed air column, which is one type of standing wave that we get with sound waves. But we can also get a standing wave in an air column that has both ends open. If we want to get a standing wave in an open air column, we need to have antinodes at both ends. Those open ends act like free points, and they can achieve a maximum amplitude in a standing wave. The resonant frequency equation for standing waves in open air columns looks similar, but a little bit different than the open closed air columns. Here we have the frequency for open air columns to achieve standing waves at different harmonic levels, and it equals n times the wave speed divided by 2L, where for an open air column, the harmonic number can equal any positive integer value, 1, 2, 3, 4, and so on. You'll actually notice that this equation is the same equation as that for a string under tension that was fixed at both ends. And this situation precisely is analogous to that string that is fixed at both ends, except this time instead of having nodes at both fixed points on the end, for an open air column, you will have antinodes in a standing wave at both ends. So what some of the standing waves look like for open air columns is this. The fundamental frequency would have a node in the middle and two antinodes at the end. The second harmonic would have a different shape. The third harmonic, the fourth harmonic, all have different standing wave patterns that are attainable, but they all need to have an antinode at both ends of the open air column. And some instruments that mimic open air columns would be like a flute. That's probably the easiest example, where there's one hole that's open and free to vibrate and let sound out, and there's another hole at the end of the flute that is open and free to let sound out. Also, the piccolo, which is similar to the flute, or oboe and bassoon, are both open air columns, as well as a pipe organ itself is an open air column. There are two places where the sound wave can be let out, this little bottom hole and that top hole. And so if we send sound waves through at the right frequency, we can get them to resonate. Just like we had for the string under tension, we will be drawing standing wave diagrams for sound waves in an open closed air column and an open air column. Remember the rules of where you need to have nodes and antinodes, and that should make it possible for you to draw the fundamental frequency as well as several harmonic standing waves above that resonant frequency. Lastly, we talk about an interesting phenomenon called beats, which is when there are two frequencies that are very similar in frequency being played next to each other. And when you have two very close sounds that are just a slightly different frequency they will interact with each other to create a warbling type of sound. It's kind of hard to emulate with your voice, but I'll try to show you in class. If you play one note at that pitch and another note, which is slightly different, at the same time, those two will come together and interact, creating some type of interference. It often sounds very dissonant to our ears, which will create a warbling like sound. It might be like wow, 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 something sort of like that. And that would be called a beat. This means that the two sound waves that are individually different are interacting to create a pulsating type of noise. They're interfering with each other. So if we look at two individual sound waves, they can be played at just a slightly different frequency, and when we add them together according to superposition, we will have spots where those frequencies have a very high amplitude and spots where those frequencies have a very low amplitude. The resultant wave will experience destructive and constructive interference at various points because the frequency, these two individual waves are close, they're just barely off, but that is a combination of constructive and destructive interference that creates a phenomenon that we call beats. And the frequency at which these warbles or these beats occur is called the beat frequency. And that will basically be the frequency at which one loud part of the warble comes to meet another loud part of the warble. So this beat frequency can be calculated, and that beat frequency will occur at just the difference between the two individual frequencies that are interfering with each other. We use an absolute value here because the beat frequency will always just be a scalar number. So you can calculate this for a combination of two sounds, or if you have three sounds being played at the same time, there will be three different beat frequencies that will occur because you'll need to do this equation for every different combination of individual waves that interact with each other. So that's beat frequency. We're going to try to deal with that a little bit more in class, but I just wanted to make sure you were aware of it. So that'll cover everything for Unit 12B. I'll see you in the next one.